Hey everybody, today we're going to go over section 7.4, the second half, so part 2. This deals with the surface area of a solid of revolution. Okay, so as we saw before, spring break, we were calculating the volume of these solids. Today we're going to talk about how to calculate the surface area of these solids, okay? So recall that a surface of revolution, basically we take a curve and spin it around an axis, then we get a solid of revolution. So let's just consider this curve here. So when we spin it around the x-axis, let's say, spin it around our x-axis, with an equivalent curve down here, something like that. Okay. So what we're looking to do is figure out what the surface area of this surface that's generated when we spin it. So this surface area here, okay? So what we can do is basically do the same kind of thing we were doing with our volumes and with our arc length, is to do an approximation of this surface area. So basically what we're going to do is we're going to partition that axis again, let's say A to B. Say this is x naught, this is xn. What we're going to do is partition it, say x1, x2, xn minus 1. In the same way that we've been doing, right? So we partition this so that all of our distances between the x values are the same. So that would be our delta x. Okay. And to approximate the surface area, what we need to do is use, as we saw before in the last video, small line segments for our arc length. We would get an equivalent line segment down here. And we see that we form a kind of conical shaped region, not quite a cone. It doesn't have the point of this cone here. But we're going to use the surface area of a bunch of these, what are called frustums, to generate the surface area, right? So we would do another one here, we would get another frustum there, and so on and so forth. So here we would have an equivalent frustum for the last one, same kind of thing, okay? So we can do so by investigating what the surface area of this frustum is, okay? So the surface area of any given frustum is equivalent to 2 pi times the R1 plus R2 over 2, the average of the two radii, times L, which is the arc length of this line that we're dealing with. So let me redraw this. So basically, let's look at this first frustum here. We have this kind of thing going on. Okay. So the radii are dealing with the radii of the circular basis. Now note that they're different, so that's why we have two separate radiuses there. So let's call this one here R1, and then this one here R2. And of course our L is our arc length. It's the length of this line segment right here. Right? It's the slant height of the cone or the frustum that we've created. Okay. So this formula, 2 pi times the average of the radii times L, gives us the surface area of that frustum. Okay. So what we're going to do is just add up all the surface areas of all of these frustums from our diagram above, right? So the surface area of the solid is equal to 2 pi times, now let's think about how we get these guys here, okay? So note that the R1 value, that would be here on our graph, is simply the functional value at that particular point, right? So this would be f of x naught. That would be our R1, let's say. And then the radius of the lower base of that first one would be f of x1, right? X1, that would be our R1, let's say R2. Okay. So here we have f of x naught plus f of x1 over 2. And as we saw before, with our arc length, L is approximated by using that distance, which would be the square root of delta x squared plus delta y1 squared. And of course, this is approximately still approximate. Plus, the second term would be similar in fashion, 2 pi times. Now, if we look at the second frustum, now the our previous R2 is now the new R1, right? So this would be f of x1 plus f of x2 over 2 times the square root of delta x squared plus delta y2 squared, so on and so forth, right? So the very last one would be f of xn minus 1 plus fxn over 2 times the square root of delta x squared plus delta yn squared. So again, we're just adding up all of these surface areas, okay? So we can do a similar technique in rewriting this formula to generate our formula for the surface area, okay? So the surface area, we'll say equals, the sum, I goes from 1 to n, of 2 pi times f of x n minus I minus 1 plus f of xi over 2 times, and I can do that bit of a rewrite, holding the delta x squared off, taking the square root and so forth, like we did in the last video. That'll leave us with this guy, delta I squared over delta x times squared times delta x. So again, I factored off the delta x squared within the radical, and then took its square root. That's what puts the delta x outside. And I'll have that kind of derivative term left over, both squared there. Okay. So this gives us still an approximation to the surface area of the solid. So we can induce a limit, taking n to infinity, to get the values that we want. So the surface area of the solid is exactly equal to the limit of all this stuff limit as n goes to infinity of this sum And now let's think about how this limit affects this guy here. Okay, so we know that the infinite sum here can be represented as an integral from the endpoints, 2 pi. Now this just becomes our arc length, right? So we saw that from last time. But how about this? What happens here? Well, notice that as the number of partitions goes to to infinity, that is, then these two f values become so close that you can't really tell them apart, right? So what happens is that this becomes 2 of the same value, 2 of f of x over 2. Once again, when the number of subintervals goes to infinity, these x values get so close that their y values are now indistinguishable from each other. So we're going to make that continuous. Times the square root of 1 plus delta dy over dx squared times dx. So finally, one more simplification. You can pull that 2 pi out. 2 pi times the integral from a to b. 2 divided by 2 is just 1, so that's f of x times dy dx is simply our f prime squared dx. So here is our surface area formula to calculate the surface area of a solid of revolution. So let's try an example. So we want to calculate the surface area of the solid of revolution obtained by revolving the graph of f of x equals x to the third about the y-axis, about the x-axis on the interval 0 to 1. So again, calculate the surface area of the portion of the graph of x to the third from 0 to 1 about the x-axis, that is. Okay. So with this, we don't really need to graph anything, luckily, because their function, our surface area formula only depends on the function itself. So we are ready to go with actually integrating this. So our surface area will be 2 pi times the integral from 0 to 1 of the function itself, which is x to the third, times square root of 1 plus the derivative, which is 3x squared, all squared, dx. Okay. Now, let's try to integrate this analytically if we can. Of course, we've added another term, so this integral is even actually more complicated than those that are for the arc length formula. But let's see if something nice happens. So let's square that one term out and see if we get something useful. So this becomes 9x to the fourth dx. Now, any technique of integration that you see can be used here? Well, notice the u substitution problem, right? U sub tells us if we make this equal to u, it's going to differentiate into something involving x cubed. So a u sub is appropriate here. So our u is 1 plus 9x to the 4th. And du will be 36x to the 3rd dx. And of course we'll need to move that 36 out there. So 1 over 36 du equals x to the 3rd dx. This is also a definite integral, so we need our upper and lower bounds here. So our bounds, upper bound will be u equal to 1 plus 9 times 1 to the 4th, or 10. And the lower bound is u equals 1 plus 9 times 0 to the 4th, or 1. Alright, so we have, let's pull our 1 over 36 out, so we'll have 2 pi over 36 times the integral from 1 to 10 of the square root of u du. Alright, so simplify here, pi over 18, antiderivative of u to the square root of u, or u to the 1/2, would be 2/3 u to the 3/2 from 1 to 10. So we get pi over 18 times 2/3 10 to the 3/2 minus 2/3. This is approximately equal to 3.56. So, sometimes we'll get lucky with this u substitution problem. Other times this will be, we will be unable to do this integral analytically because none of our techniques would fit to it. Let's try one more. Alright, so here let's set up the integral to calculate the surface area of the solid of revolution obtained by revolving f of x equals x squared about the x-axis from 0 to 1. Right. So let's take a look. Surface area will equal 2 pi integral from 0 to 1 of f of x, which is x squared, times the integral of the square root of 1 plus f prime, which would be 2x all squared dx. So that's basically it. Now notice this integral gets a little tough actually. Plus 4x squared dx. Because u substitution is not appropriate. In fact, we would have to use a trigonometric substitution embedded with like an integration by parts at some point in time. So let's just use our calculator to try to get it. So using our calculator, okay. There we go. There's actually a built-in feature for your calculator. If you go to Math, hit Math. Barely see that. You hit Math. And then go down to the 9th option. The 9th option is fn int. And it should give you a nice integral like that. Sorry about the visibility. But we can input our integrand as we have written it there. So I'm going to go in front and insert a 2 pi there. And then go for it. So 0 to 1, x squared, square root 1 plus 4x squared. And then x at the very end, right? So you have something like that. 2 pi times the integral from 0 to 1 of x squared times the square root of 1 plus 4x squared dx. And let's see what we get. 3.81. So once again, hit math. That's here. Math key under alpha. Go down to the 9th option, which is fn int, and then input all your stuff there. Okay. All right, that does it for this lecture. So you can try the suggested homework problems in the book. They're much like this. Some have you actually go through and do the calculation. Some have you just set it up. But go ahead and do those. If you have any questions, let me know.